Okay, rockets and rocket science. So when they say, well, it's not rocket science, well, it's not rocket science until it is, and now it is. And the one thing I do want you to know right from the start is that rocket science, rocket propulsion, which is what we're looking at in a very fundamental way, is really conservation of momentum science. When a rocket goes forward, it goes forward because it is ejecting fuel out the back. So what we are looking at with rockets is always a rocket fuel system. So there are no external forces. Our rocket we want to think of as in outer space, isolated, away from any planets or stars, no external forces. So the only way this rocket can go forward is to eject fuel out the back. So conservation of momentum says, well, let's consider if our rocket was initially at rest. We're going to eject fuel out the back, and the rocket is going to recoil forward. So that is how rockets move. It's a conservation of momentum event. So as the rocket moves, it's no longer at rest. So now the P initial that we have in general, so for our conservation of momentum, our P initial for the rocket fuel will be capital M times V, and I have up here the variable indicators. So capital M will be the mass of the rocket and the fuel at any given point in time. V will be the initial speed that we're dealing with as combustion occurs, and we're now going to get a change in that speed. So the speed is going to increase by an amount dV, so that's what I have here. So please get all these annotations into your notes. So the speed increases to V plus dV. The mass, particles thrown out the back, are going to be calculus point particles. So that's our differential mass being thrown out the back. So that's the dm equals differential mass. What is really important, again, is manufacturers of rockets, just like manufacturers of munitions, specify the rate at which fuel is being ejected, the speed of the fuel being ejected, as a muzzle velocity. It's always with respect to the recoiling rocket. So we've dealt with muzzle velocity before. So the speed of the fuel is always from the perspective of the rocket, so it will be greater than the speed of the fuel that we need in our conservation of momentum, because that has to be with respect to the inertial observer. And that is what I have down here. If you remember from our cannon problem, it was 55 minus the speed of the cannon. Well, here we have the muzzle velocity, which is the speed of the fuel, right? The U here. And now instead of the speed of the cannon is not recoiling, it's the rocket recoiling, and it's recoiling, its speed is V plus dV. Same concept. Well, all right, the differential mass of the fuel that was ejected out of the back is also going to give us the term we need to calculate the decrease in the mass of the rocket fuel system. So that's why we have the minus capital M minus dm here. And all we have to do is all of the algebra. So we have first, inner, outer, last over here, and here to give us all of our terms down here, our first, inner, outer, and last, give us those four terms, and then we just distribute the dm through to get the last three terms here. The mv is our mv over here, and as you can see, we get a ton of cancellations. Almost everything cancels. The only thing we're left with is the m dv and the dm times u. So that is where this equality comes from. And if we look at what we have here, we have the dm is the differential mass of the fuel, the u is the speed of the fuel, the capital M is the mass of the rocket and the fuel that were recoiled forward, and dv was the increase in the speed of the rocket forward. So this statement has units of momentum. So basically what it is saying is the momentum of the fuel backwards must equal the momentum of the rocket forward. We have one other little piece here. We have two different m's, and we're going to reconcile that by, again, reminding ourselves that the fuel that was ejected out the back will correspond to the decrease in the rocket mass. So that's the minus dm here. So we are finally at the bottom line, which is often the bottom line of the page, where we have our conservation of momentum equality for rockets, and you are just going to memorize this. Anytime you have a rocket problem, you are going to simply write down negative dmu equals capital M dv to start any derivation or analysis that you're going to be doing with rockets. You do not need to prove it. The only thing you might need to do is to justify it by saying that this equality is a conservation of momentum statement for rockets. You need to understand that the left side corresponds to the ejecting fuel out the back, and the right side corresponds to the rocket going forward, the momentum going forward. So you will not be responsible for the derivation that I just went through with you. I could have just given you the equation at the bottom of the page, and it would have been some just mysterious, I have no idea why that is the way it is equation. So it was not that difficult for you to see the derivation, so that is why I show it. But you are just going to use that equation to problem solve from this point on, and we are going to do a couple derivations in our next lesson.